Hello everyone, my name is Zaire,
Hi, and I'm Grace.
and we're your RAP leads. So, what is RAP? RAP focuses on the wireless communication of bits from one communication platform to another. So for example, we have a transmitter and a receiver. How do we get communication between the two? How do we send messages across, and how do we meaningfully extract information out of it? So to start off with, we need to actually design a transmitter. And to do so, we have to delve into what does a transmitter do. So we start off with data, and we take that data and we need some way of encrypting it. We need an easier way of converting that information held in that data into some other format that we can then send out to the hardware. But to do so, we do this through a process called digital modulation, in which we encode our digital data, our ones and zeros, as some form of encryption. So over here, we can see that there is a phase shift between 1 and 0 when we go, in our sine wave, when we go from 1 to 0 of 180 degrees. That's one type of modulation. There's various other types that maybe you learned like 132A. Next, we have to send this data out to our actual analog hardware into the real world. In the real world, we don't deal with digital, we deal with analog. So we need something to bridge the gap between the two. This is where our digital to analog converter comes in, which we use under a microcontroller. After this, we want some way of up-converting this. The reason we up-convert is because if we have an antenna at low frequencies, it'll be very, very large. And that's not very feasible. So instead, we just like up-convert it to 27 megahertz, which results in an antenna wavelength of around 11 meters. So this is much more feasible. Despite the antenna length being 11 meters, we end up using an antenna of around a foot long. So we need some hardware to actually up-convert to that frequency. Next, we feed that into an antenna, it gets broadcast through the air, and then it gets received.
Yep, so as our signal is traveling through the air, it picks up noise, and it also, unfortunately, gets timing offsets and synchronization offsets that we then have to deal with on the receiver side. So in addition to having our signal down converted from 27 megahertz back to 1 megahertz, which is what our MCU can process, and converting that down converted signal back into digital data for our MCU to process. What we need to do then is basically the process in reverse, except with some extra steps to deal with that noise and that timing offset. And hopefully, if all goes well, we get the data that we sent originally. So now we have a quick video demo.
Alright, so coming to you live from the IEEE lab, here we have the transmitter set up for RAP, and then we have it connected to the microcontroller, which is connected to Dom's laptop, which is connected to your keyboard input. So Dom, why don't you type us out a message real quick? Okay, so we typed out I love, and then on the other side here, we have the receiver side of RAP, and then all the way connected to the other microcontroller, connected to my laptop here. And then now on this side, we see from the UART input, from the UART output, we see I love. And then Dom, why don't you give us one more message? I love, what is that? I love rap? Whoa!
Cool. And then if you'd like to see our demo live, we will be tabling outside. But now Zaire will go into more of.
Alright, so coming.
Zaire will go into more details on the hardware.
Yeah, we'll save Nathan that uncomfortable experience again. So yeah, RAP hardware, what exactly is it? It's basically us diving into the physical realization of our communication system. So over here's a few pictures, and it looks kind of scary, but I'll kind of walk you through what you do in RAP hardware. So first we're going to talk about designing schematics built off of the block diagrams we need for communication systems. So we need like amplifiers, we need filters, we need mixers, etc., etc. So we go from the block diagram to physical hardware. How do we talk about making that? Well, we actually have lectures that go through all the theory and the applications, and we'll give you a module after that will kind of walk you through what you need to do to get a realizable module. So over here in the top picture, you can see us kind of testing out the transmitter, and it's basically all modular. So you can see that we have an amplifier, a filter, a mixer, then we filter, amplify, and then output. And we can bring that into a spectrum analyzer. That's one of the tools we'll use. And over there in the bottom corner, we have a nano VNA, and that basically tells network parameters, so stuff like impedances, reflections, gain, etc., etc. spectrum analyzer for frequency measurements, because at the end of the day, we want to verify, hey, we get a signal out at 27 megahertz. So those are two tools that we use. We also use oscilloscopes quite often, and over there, the big thing on the left is a signal generator. So with our RF hardware, we're going to be actually physically assembling things, debugging, testing it out, and actually using RF test equipment that you don't really get to use on a day-to-day basis. On the bottom left, we see our finished RF transmitter hooked up to its MCU, and you can see that it's looks a little daunting, but when it's all put together, it's pretty seamless, as you can see outside. And on the bottom here is something that I've been looking into as more of an R&D aspect of RF. It's a direct conversion system. So what's happening in our basic system right now is we go from a 1 megahertz signal at our MCU, up converted to 27 megahertz, get transmitted, receive at 27 megahertz, down converted back to 1 megahertz, and then sampled at twice that rate. So that's kind of cumbersome. It takes up a lot of processing speed, and it's not the most efficient way of doing so. And right now, software is the biggest place we can improve our performance. So to do so, if we can go down to a lower frequency than 1 megahertz through a mechanism called direct conversion, then that's better for our software end. And of course, when you have a different hardware topology, we can actually implement that. So that's what I've done here in the bottom right. And for here, we can see a simulation we've done in LT splice. Again, looks a little scary, but we'll talk about each one of these blocks. For example, the one on the left, that's going to be our Colpitt's oscillator. So we need to generate, sinusoids that we use to mix. And being able to generate a clean sinusoid is very important because we want one specific tone. And we don't want any intermixing to occur. We don't want any of these, other frequencies to interrupt. So we want as clean of a signal as possible that we can generate. That's what an oscillator is. Of course, we have our buffers and amplifiers to make sure that things stay isolated and perform as expected when we hook these things up together. And then, of course, amplifiers to amplify a signal. We have our mixers right there in the middle that perform up conversion. And then we have the filter, 5 megahertz over there. Another amplifier stage, a buffer, loops all the way back down over here. And then that same process repeats up to 27 megahertz. And then boom, it's our antenna. So it looks a little scary because this is just one half of our whole hardware system. This is this transmitter. But the great thing is the receiver is just this, but flipped, pretty much. So once you kind of get the hang of, how the different things fit together on the transmitter, you just flip it and you get your receiver. And it's great because it's all modular. And being able to piece everything together and go piece by piece and see it all fits together into a working communication system is very fruitful, especially when you take certain classes and you dive into the theory, but when it comes to actually stringing concepts from like 5, 6, 7 classes together, you don't really get that in a 10-week course. So it's really nice to see things from like circuit classes, your 141 classes, communication classes, and obviously your 102 classes all put together into one kind of project. So over here, a bit more of the testing aspect of RAP. It's not just us kind of sitting on a bench and soldering and messing around with resistors. It's a bit more involved than that, although at times when it comes to debugging, you gotta mess around with resistors. Over here we have an oscilloscope of our VPSK signal. So VPSK is a type of modulation, and we can see that's our waveform. So that's our H ASCII characters being repeated, and that's our VPSK waveform for that. That's us verifying that, hey, it's actually up converting properly. We see our actual waveform, and our signal and our message is intact, our information is intact. That's the important part, is when we actually send data through hardware, we want to make sure our information is intact, it's preserved. At the end of the day, we want to be able to send a signal out and not have it be affected and corrupted. And over here on the right is a zoomed in picture of a nanobeam. Sorry, your left, my right. I mean, your right. And again, you can see this for filter. We have in the blue curve, you can see it's S21, and that's basically telling you, it's forward feed through gain. And we can see that, hey, it's a bandpass filter, and it's at 27 megahertz, we expect it to peak. So that's great. It's S11 is low, that's acceptable. And this is another way of us to verify our theory. We make something, we have to test it out somehow. And how do we test it? We have instruments that do so. So understanding how to use the instruments is something that we will explore in RAP. So pretty cool. And another part of testing, this here is retesting a mixer on the spectrum analyzer. So mixer is going to be a frequency component. So we want to test it in the frequency domain. So you're going to feed in 2 signals, you're going to look at the output, and hopefully everything goes according to plan. So when it comes to the mixer, it's very, very finicky, it's very sensitive. So making sure that when you make it correctly, and that it is as stable as possible is the goal. And this in particular is a bell balanced mixer. So you can see the harmonics of the yellow go away. Those are just words, I'm quite sure for a lot of you, but you'll actually learn about what that stuff is, why it's important, and get to see it actually done in real life. But it just goes to show all these past 2 slides that, we do mess around with real life things, not just resistors and capacitors. You mess around with these very interesting pieces of test equipment that you never really get to touch, and you get to go pretty high enough in frequency that you get to actually see some of the more nuanced parts of hardware, which is really nice. So yeah, you get exposed to various parts of RF and analog design alongside system level design, and again, getting used to oscilloscope, spectrum analyzers, and network analyzers is very, very pivotal for anyone who actually wants to, pursue any sort of, hands-on electrical engineering field. Numerous times I've had people ask me, how do you use a network analyzer, how do you use a spectrum analyzer? And, well, I wouldn't know how to do that without RAP. So, very useful experience. And R&D for direct conversion. I talked a bit about this before, but this is something that I've done this year. And it also alleviates the strain placed on the DSP side of things. And at the cost, it's more complex on the hardware side. There's not as many moving pieces, but the moving pieces themselves are more complicated and sensitive and harder to get right. Over here, I have a picture on the bottom. You can see that there's an LNA, and the bottom of it got cut off, but that's an IQ generator here. And next we go into the mixer we've seen before, a low-pass filter, and our DSP block, and we have a voltage controlled oscillator as opposed to just a normal Colpitts oscillator, free-running oscillator. So it's hopefully a more efficient method of doing the same thing that we have outside. And that's it for me.
Cool, yeah, now for the software side. So during fall and winter quarter, the students completed a few different assignments that would teach them the basics of digital communication. And then during spring quarter, each of my lovely students chose a particular aspect of the RAP system to improve upon, and then they'll be presenting their R&D work. But before that, just so that I can get y'all on the same page, I'll be explaining a high-level overview of what the software does. So at its core, we need some way to encode binary bits, just a bunch of ones and zeros, onto a 27 megahertz sinusoidal carrier wave that will travel over the air. So there's many ways of doing this, but one is basically choosing a particular phase of the sign in order to, so we'll say, we'll assign a binary bit of 1 to a cosine with 0 degree phase offset, and a binary bit of 0 to a cosine of 180 degree phase offset. So what you get is this interesting kind of like shape with M's and W's whenever there is a transition. This is called binary phase shift keying. This is, for example, like one of those interesting phase transitions, which we'll see in a bit. Now, to actually implement this, we have a very high-level flowchart here. The first step is mapping our bits onto what are called symbols, which in our case is just negative ones and ones. So we convert our zeros and ones to negative ones and ones. And then in order to be able to transmit this signal, we need to give it some kind of like sinusoidal shape. So we do this convolution with a function that will be able to retain our symbols at each point that we care about. And then we'll multiply this new like orange wave with a higher frequency wave to be able to transmit it. It's hard to see because it's very high frequency, so let's zoom in a bit. And I am looking at this bit transition here from 0 to 1, and you see, we see this kind of like weird M shape where the phase flipped. So then after that, the signal travels over the air. You can see this N of T represents the noise. And in addition to picking up noise, the signal will also experience a timing offset, which we'll have to deal with on the receiver side. So things like carrier synchronization, timing recovery, and some fun diagrams to analyze that, which I won't go into yet. And then also frame synchronization, which another of my students will chat more about. And then hopefully at the end, we receive the bits that we sent. So now I'll hand it off to Nathan to explain more about the MCU.
All right, yeah, thank you, Grace, for that lovely introduction for what we're doing on RAP software as a whole. But personally, what I and Dominic over there is going to talk later, what we worked on was mainly just taking our theoretical MATLAB simulation codes of this communication system and actually implementing those algorithms that we've typed out into our embedded microcontrollers, one of which you can see up here. But like with all these theoretical MATLAB simulations, theory will only take you so far, because when you actually move to a real system, you run into things like, oh, like how fast is the microcontroller actually processing? Like, oh, how much space do we have on our microcontroller? Like, does it have enough RAM to fit all of the things that we saved at once? So when we were faced with this, we had to kind of like come up with creative ways in order to like work around these things and create our algorithms such that they were processor efficient and RAM efficient, so we could do everything that we wanted to do on these microcontrollers. And for these microcontrollers in particular, these are STM32H7 boards, and they are much more powerful than the ones that we've had in previous years. So using them, we were able to push the limits of what our RAP system was able to do this year. That including like being able to send multiple strings of characters at once, and also pursuing other R&D topics such as like channel coding, and then channel coding, multi-character strings, and then better time recovery, which these people over here will get into next.
Hi, I'm Dominic, and I'm just going to talk briefly about some of our recent efforts to log more raw data. So basically kind of what I did was modifying our existing receiver code to send the raw samples from the ADC over UART, and then I wrote a script to capture those on the computer. And so, because previously the system transmits and then receives and it does all the signal processing on the embedded side. So we don't really have good visibility into what exactly was happening. So this is kind of useful for debugging, as well as potentially validating and understanding the RF front end, like to see if there are any spurious emissions, or seeing if there's carrier frequency offset, things like that, being able to do all that analysis offline. We can also evaluate DSP algorithms, testing ones that we've already implemented, like timing recovery and channel coding, but also maybe other things like higher order modulation schemes, and then also getting better understanding of like the channel in the system itself.
So hello, my name is Brandon, and one of the new things we're doing with R&D is channel coding. So we don't receive the bits. Unfortunately, at the receiver, we don't receive the bits exactly as we want them to. As you can see on the top, these are noise. We end up receiving a bunch of corrupted bits, and you can see it in this image below. We don't get the characters exactly how they want. So the solution to this is to introduce channel coding, which is to introduce redundant bits to our message so that we can do some error correction to it. And so, as a result of this, as you can see at this image at the bottom, we're able to turn our corrupted characters into basically readable characters saying I love rap. Now, for our implementation, because it's our first time doing channel coding, we just focus on simple error correction codes such as repetition codes and Hamming codes. But in the future, now that we got this done, we can hopefully do more sophisticated codes, such as either turbo codes or LDPC. I'll pass on to you.
Hey everyone, I'm Kaden. I'm just going to spend a minute talking about timing recovery, why we need it, and what it is. Now, when we send a signal from the transmitter to the receiver, there's some finite time delay just from the wave to propagate. This is called a timing offset, and why this matters is that our signal, we have to sample it. We basically have to pick out points where we want to say this is a 1, this is a 0. But if we do this very naively, we can do it really badly. If you guys see these purple dots kind of right there in the middle, they can often be very close to 0. That means they have a lot of, or are very sensitive to noise, just generally hard to cleanly separate. To show that better, here's what it looks like when we try and just naively sample the signal coming in without like a smart algorithm for timing recovery. This on this side, it's pretty much impossible to just cleanly draw a line through that. However, we can implement a phase-locked loop algorithm to essentially catch and then track what that timing offset is. And if you see here, all these these symbols are very cleanly separated, and we can draw a nice line to delineate a 1 or a 0 bit. I'll hand this on to Kevin.
Hi, I'm Kevin. I'm going to be talking a little bit about frame synchronization. So right now, we've done a lot of error correction codes and stuff like that to make sure our bits are received properly. But really what we're doing so far is just yeeting some symbols through the air. we don't really know where the method starts. So to solve that, we have to figure out a packet header solution or a key. And the way we do that is we implement a cross-correlation algorithm that tells us where the method starts. So as you can see there, when the cross-correlation hits its peak, we know that's where the method starts. And we do that with something called barcodes. And this barcode is a lot more efficient than what their implementation last year. It's more mathematically sound, and we've done a lot better. As you can see at the top there, there's a peak at the very start of the message, and that's where we know where to start decoding our message, where to start applying our error correction codes, and all our other binary digital modulation schemes.
And that's a wrap. Thank you.